Now that we have kind of discussed the basic principles of how we move from a correlation coefficient to some sort of regression line in an actual regression analysis, I want to kind of step back a little and think a little bit more formally about how we're going about drawing this best fit line. It's not necessarily just that we have a linear relationship. That certainly is an assumption that we are making, right? So again, we're saying that y and the expected value of y is a function of our intercept and then some sort of angle of that line. But we also know that that line isn't going to be a perfect model for the data generating process, right? There's going to be some uncertainty or error in that model that we want to incorporate. And so we're going to actually write the regression line as such, where y is not only a function of that alpha and that beta times x, but now we've incorporated some term of error. So we're adding an additional assumption here that this error on average, again, this is important, on average, the errors equal 0, and that the variance of those errors is equal to the sigma square. And we're going to measure what that sigma square is in the sample to create an estimator for this parameter. So we can rewrite our equation then that y is going to be a function where it is normally distributed at alpha plus beta times x, and it's going to have a variance equal to sigma squared. Now, I know this can be a little confusing at first, so I just want to remind you what the assumptions that we've been working with so far are. So what we talked about last week, right, is that we need to have randomized data generation process, either through an experiment or an observational study. And these observations need to be independent from each other, right? So if we're taking a survey, my answers aren't going to are going to be independent from your answers. What I'm answering isn't affected by what you're answering. Now, what we're introducing today is that we need to have a linear relationship. So more formally, what that means, right, is that the population means for different values of x have to basically go through a straight line with x. Now, that sounds a little confusing, right? But essentially what I'm saying is that the conditional mean of y at different values of x has to be a function of this linear line that we've drawn. Now, we also are making an assumption of normality and constant variance, but this is with regard to the errors. So what we're saying is that at different values of x, the values of y are going to be normally distributed, and they're going to have the same standard deviation for each of these different values of x. That's where the constant variance in y is coming from. Now, I think it's a lot easier to see this with an example. So what we see on our y-axis, right, is 5 different values for x. On our y-axis, we have our actual value of y. So it's literally the expected value of y given a certain value of x, which we are expressing as alpha plus beta times x. And what you can see here is that for each of these distributions, each of these conditional means, we have the same expected variance. So the shape of those bell curves looks the same, right? And they are normally distributed. And they all have the same conditional mean as a function going through that regression line. Now, I know this can be a little bit confusing, so what I'd like to do is to actually show you what data would look like if it were to have perfectly distributed normal errors. So we're going to first just create our data. We have created our x variable from a random variable coming from a uniform distribution, there's going to be 100 observations in this data set. Then we're also going to create our outcome, and we're embedding in what the relationship is so we know how far away we actually are with our model, right? Because there's inherently going to be some error that's baked into the data generating process. That's what this additional term here is. What I'm doing is that I'm making sure that our assumptions are met. The errors are going to have a mean of 0, and they're going to have a standard deviation of 1. Now, we go ahead in the last line and run our bivariate regression to see what the association or the estimated association is. Notice that we have an imperfect model of the true relationship between y and x, right? We've added in some error. But what's important is that the error that we've added in, we're assuming has a mean of 0. So on average, it shouldn't make too much of a difference. So what you see is that we're able to get pretty close when we estimate what the true underlying relationship is between x and y. We know from before, right, that we said the line should cross at 2 and the relationship should be positive at 1.5. In our estimated model, we see that the relationship is around 2 going through the y-axis, and then the relationship between x and y is about 1.5 at 1.72. But again, there's some error in that. So we're not getting exactly the true relationship. We're getting close. Now, if we added in more and more observations, we would find that we're going to get closer and closer to the correct or true underlying relationship. What I want to do here is I want to show you what the residuals look like for each of these values of x. And so we can see that sometimes it goes a little bit above what the regression line is. Sometimes it goes a little bit below what the regression line is. So for each observation, we have some sort of measurement, how far away our predicted value based on the regression is at that line from the actual value that we observed. And it might not necessarily look good, but if we look to see what the error is in expectation, what we actually find is that it's not too bad, right? We've met this assumption that on average, the residuals are centered at 0 and have a standard deviation equal to 1. So essentially what we've done is we've reduced all of the data down to some sort of simplified model, right? We're not going to get it right every time, but we want to get close and give our best guess as to what the true values of these 3 parameters are, right? So we need to estimate using our data what those parameters are. Once we have our parameter estimates, then we're going to want to make some inferences. And in order to make some inferences, we're going to set up hypothesis tests. And just like before, we're going to summarize how well the data actually end up supporting these hypotheses. But before we can do any of that complicated stuff, we need to actually go ahead and justify how we choose our estimates or our estimators of these population parameters.